I think we'll give people another 2 minutes to join. We had close to 150 registrations, and people are still joining in. So let's wait.
Sure.
In the meantime, maybe we can just do introductions. I am Reena Dayal. I am the chair for the Quantum Ecosystems and Technology Council of India. I'm also the founder. The purpose of QETCI, as we call the entity, is to enable and empower the ecosystem for quantum in India. And we are a membership-based organization. So we have companies like Amazon, Microsoft, and Reliance Geo platforms as our large voting members, and a lot of individual members as well as some startups that are associated with us. This hackathon cum incubation effort, which we are calling the Quantum Science and Technology Hackathon, we are organizing as an intervention to stir the ecosystem, generate more interest in this area, and specifically looking at the strengths that India has in terms of the focus on software and the kind of skills that are available with people. We feel that this is the right time to invite more and more people to be working in this space. Apart from the prizes that are there for the hackathon, for for the projects that people come up with, we are also enabling. There are companies who are sponsoring and who have come in primarily with the interest of talent, right? So anybody who works on a project, on a use case, and is able to take it to a certain level of a proof of concept, etc. Not only do they have an opportunity to be winning a prize as part of the hackathon, but they will also have an opportunity to be able to look for internship opportunities or job opportunities. This is critical in the space of quantum because we have a chicken and egg situation in the market. Most people are looking for people with some experience. Most companies are looking for people with some experience, and people are looking for where to gain experience, right? So this is also a way for you to gain experience, and through your project, demonstrate that experience. And it's easier for people when they are looking at your project to understand what your capabilities are. So while that's not the primary purpose of the hackathon, that is also something that has, emerged from this effort. And today, while as part of the organizing committee, we were having a conversation with folks in terms of what else can we do to excite people, and some of the things that came out from the various outreach to folks, to prospective participants, we realized that there was a need for giving some ideas on the kind of use cases we are seeing across the world, so that people's imagination can be sparked, and it becomes easier for some people who have not yet thought of an idea to really zero in on an idea, right, and take that forward. And Sachin Punyani from Amazon, Amazon Web Services, he's actually very kindly offered to do a session on use cases and spark some discussion today here. So what I'm going to do is tell you a little bit about who Sachin is. Sachin leads the business development for AI, ML analytics, IoT, HPC, and quantum computing for India and South Asia with AWS. And is helping AWS customers in modernizing their applications by integrating AI, ML, and IoT capabilities in their business solutions. He has helped multiple government. Somebody asked for transcript, sorry, so that has been enabled. Sorry for the interruption. He has actually helped multiple government and industry organizations blend their domain expertise with new technology to build solutions that have citizen impact. And there's a lot of certifications that he has and 16 years of experience. So thank you, Sachin, for being here. And one of the other things that I wanted to point out to participants before I hand it over to you, Sachin, is that both Amazon and Microsoft are providing their platforms for and people who can support your queries related to the platforms. So a lot of mentoring that will be available as we move forward. And right now, I think I would recommend make best use of this session. Keep posting your questions on the chat window so that we can take that up as we move forward. Over to you, Sachin. Thank you very much for being here, and please, over to you. You're on mute. Is this?
Can you hear me now?
Yeah.
Thank you very much, Reena. I just turned the camera on for some time, and if there are bandwidth issues, then I'll shut that out. But for now, I'm just keeping it on and sharing my screen.
Sure.
Can you see my screen now?
Yes, I can see your screen. Please go ahead.
Thank you. Hi guys, thank you very much, Reena, for this opportunity to share what's happening right now in the quantum computing world and what could be the possible use cases. So how we will structure this session is like we'll just try to set up what the current quantum computing ecosystem is, what type of problems people are trying to solve, because quantum computing has different ways or different approaches of building applications on that. So we'll just try to set the context. For people who are very new, they should know what exactly is the change that is happening from the classical system to quantum computing system. So we'll set the base initially, and then we'll move on to the use cases so that you can relate that why those use cases were chosen for the quantum computing and what similar things you can choose and what quantum computing approach you can think of when you are working for some solution for this hackathon or maybe for your future use cases as well. So just starting on that thread. So there are so much hype around this, and there are so many technical and non-technical jargon. So if you see all these words that you see here, qubit, annealer, Hamiltonian, all those words, we will not go too much in technology. We'll try to make understanding as easy as possible, but we'll also try to at the same time say that what change does quantum computing bring in. So just to start, this technology actually has a potential to disrupt. This is where we are setting the expectation, and then we will come how. So there are certain problems which cannot be solved by the classical systems, cannot be solved when we say means there might be some problems which do not have a solution yet. Algorithms are not defined, or maybe if the algorithms are defined, they are not possible in the polynomial time or in a time which is practically possible. For example, if a problem is taking 100 years to solve or maybe 1,000, 10,000 years to solve, we call them unsolvable because we know that they cannot be solved in our lifetime. Quantum computer brings in a new way of I'll say setup or hardware or new way of doing things which can solve those large problems in much lesser time. So maybe 100-year problem can be solved in 1 minute, 2 minute, 3 minute time. So this is the potential disruption, but at the same time, not all problems can be solved by quantum computers. So right now you can do 2 + 2 4 very easily on a classical computer, but quantum computers are not meant for 2 + 2. So what problems are they meant for? So if you see different industries, in logistics industry, if you see, people have very big challenge of traffic routing, proper way of telling that, okay, what route should be taken by the traffic, how the network should be optimized. In finance, people might say that how the portfolio should be selected, how should it be optimized for better returns, or how should it be optimized for the lower risk. Similarly, for the pharma industry, they might see that how better drugs can be discovered with the least risks to the patient. So multiple use cases, and machine learning, of course. But if you look at all these use cases very carefully, you will find that majority of the use cases actually look like some optimization problem. Either you are trying to maximize something or you are trying to minimize something. You're trying to optimize traffic routing. You are trying to maybe optimize, or you are trying to minimize the cost or maximize the payload that you can carry on a vehicle or a ship or cargo. Portfolio selection, best returns or risk minimization. Machine learning also in itself, we all know, is an optimization problem inherently. So majority, of the problems are optimization problems, at least on this screen. So just setting the context. Now, moving immediately to the technology part. So what exactly is quantum computing doing? We'll take just a couple of slides to set the context, and then we'll move ahead on this concept. So in the classical computer, we know that there are bits like 0 and 1. So you have 8 bits that make byte, and then effectively you write your algorithms on those multiple bytes, very high level algorithms as well, and you flip the bits. There is a voltage where, below that threshold you call 0, above that you call 1. This is the basic fundamental change in the quantum computer. Instead of bit, you have a qubit. So if you, not going into the technical terms, but if you see the sphere on the screen, so this sphere, the qubit has a value on this sphere. Any sphere, any point on this sphere can represent the value of the qubit. So the value can be 0 or 1, or can be anything else on this sphere. So qubit can have multiple values. Similarly, in the classical computer, you have multiple bits. You make byte and the larger memory. Here you have multiple qubits. Some advanced concepts do come where in classical computer bits are independent, but in the quantum computers qubits are quite entangled. So we are not going in those concepts, but just saying that this is the fundamental change that is happening, and the operations that you perform on the qubits certainly change because the fundamental concept changes. So what is the potential here? The potential here is that the RSA algorithm, the algorithm which is the base for today's security, password encryption, which we see that cannot be broken. But if we have 10 million qubits, assuming that 0.1% error rate, this can be broken. Some other simulations that we have, they can also, which are not possible on the classical computers, can be done. If you see scheduling problem that we said cannot be solved, it's either NP hard or it might take hundreds of years. Those problems can be solved with 500K qubits very easily. So the problems which actually were unsolvable, again, this is giving you an example what kind of problems be there. So the problems that have been unsolvable on classical computers can now be solved with an assumption of 0.1% error rate, which is very high. The classical computers do not have this much of the error rate. Now, just touching on the error rate, the different operations that you perform in classical computer from 0 to 1, 1 to 0, you know that when you are performing an operation, the operation will, what result will it give you? But when it comes to quantum computers, you are also applying the same operation, some operations on those qubits, and you expect some output. It might happen the output is not as expected, it has some deviation. So this deviation is called error. Why is that error? The technology that is right now used to create different quantum computers, people use different technologies, that is not yet mature enough, that is not yet stable. So there might be some error. But if we try to take the analogy with the network today, so if you try to communicate some message from between two computers, typical networking, we know that there can be some noise on the network, on the channel, whether you're using air network, Wi-Fi, Bluetooth, or maybe you're using some Ethernet, anything. So all these network protocols already have error correction and error detection and error correction in place inherently. Same things you have to apply error detection and error correction while writing the quantum computing algorithm. So that error might happen, but you need to take care of that, okay, there might be an error, how to detect that, how to correct that to bring the right output. Now, why do we not have, so we did talk about some like large number of requirements for the qubits. So if you see here, the RSA, as we said, will require 10 million qubits with 0.1% error rate. But if you have pure qubits, that means 0% error rate qubits, then you might need 6,000 qubits. But why do we not have so many large computers around? Because people are building, but at the same time, the solutions require some error correction. So those algorithms, not many algorithms exist. People are right now working to create different algorithms. So this actually sets the base for first use case. If people are building algorithms that detect the error in a better way, that correct the error in a better way. So this could be one approach that different scientists, different people are trying. People are also trying to implement new algorithms that can solve. For example, here we are talking about breaking the RSA. Similarly, there might be many more algorithms which need to be written because quantum is new, so not many algorithms exist. So those things are required. So currently we are in NISQ, as we say, so noisy intermediate scale error. That means we know that quantum systems are not right, not stable yet. So 0.1 to 0.5% error rate might be there, but we know error correction, error detection can be done. So systems can be built. So where do we stand right now? So if we start dividing the eras, so the first era that you see here is the era where quantum systems physically did not exist. People had the concepts of quantum and they tried to simulate on the classical system. But the requirement of classical quantum systems is so high, the RAM requirement, that they can simulate up to a limited number of qubits only. So then in the second age, they got the quantum systems, which is the second age, as we say, NISQ, but with error rates. And the projection or the intention is to reach to the third stage, where you have better qubits as you go down the line, where you have better qubits and you have more number of qubits, so that you can solve better, you can solve even bigger problems with less overhead of the error. So right now we are at this stage. So most of the applications that you will see will be built at this stage only. Now, how to use quantum computers? Like we said that it cannot do 2 plus 2. So just taking another analogy to suggest that how to use quantum computers. If you do machine learning, we know that people try to do machine learning on CPU, but to get better results and better training, better inference, people try to switch to GPU as well. So GPU becomes a co-processor. So what happens there is that people try to run some part of their machine learning algorithm on CPU, then they pass on the load to the GPU. GPU does its own job and the results are sent back. So CPU and GPU work hand in hand, while CPU remains the primary processor and GPU becomes the co-processor. Similar ways, if you want to do machine learning, if you want to solve machine learning problem, so CPU will remain the primary processor and workload will be offloaded to QPU. The difference here will be in the machine learning scenario or in the CPU GPU combination, both the processors, both the chips might reside in the same machine. Maybe I have a laptop with CPU and GPU together, while QPU is not just a small chip, it's a completely separate machine. So it will be a separate machine altogether on the network. So CPU based machine, maybe my laptop, maybe some server, remains the primary system, and the information wherever required, QPU information is required, it is passed over the network to execute to the QPU and results are taken back. So this is the way most of the algorithms, most of the solutions will be developed. So we call this hybrid, or rather industry calls this hybrid. So current solutions will be in the hybrid mode, or maybe in the long run, it might happen that it continues to solve problems in the hybrid mode only, because QP, like we said, the different kind of problems that QPU targets actually can be it is specialized processor, so it can solve some kind of problems, and for our day-to-day routine applications, CPU are doing good. So in the long run as well, the hybrid applications might continue. Now this is the current scenario, this is the current application. Now moving to the solution side, how to build this solution. So there are two approaches or two technical directions for quantum computing. So one is universal quantum gate. So we understood there are qubits. There can be multiple qubits in a quantum computer. So in the classical systems, you have multiple bits and you apply operation on those bits and you get the output. So that is the quantum. We'll go in detail on the universal quantum gate system. Similarly, there is quantum annealing system. We'll try to understand both these systems. So how universal quantum gate system work? So you have multiple, so take the example of the classical system where you have multiple bits. You apply some operation, maybe AND operation, OR operation, then you apply the output on those operations. Effectively, you get some output. So you have a bit combination of say 101, and then you apply these operations and OR and other operations, and you get the output. So this is called a gate-based model. You create a Boolean circuit. Exactly same way when you have qubits. Now the qubits have value which is on that sphere, multiple qubits put together. So entangled qubits, so it becomes a vector, and then you apply some operations on that which work on vectors. But effectively the concept is same, that you are applying some gates, some operations on those qubits, and then you are joining them together. So effectively, you are creating a quantum circuit and you are getting the output. So this model of programming for the quantum computers is called universal quantum gate mechanism. So this is one way of doing things. Second approach, like we said, is quantum annealing. Now, in the first universal quantum gate ecosystem, you have different qubits, and then you decide what operation to do, which qubits to join together for those operations. That's on you. So it requires some effort, some what operations to apply, some programming effort. While the other system is where there are large number of qubits and they are joined inherently with some topology. So how they are joined is decided by the manufacturer of the annealing system. They decided that, okay, what topology, in what fashion should those qubits be joined? And then you decide what equation to solve. So if you want to solve some optimization equation, you decide what optimization equation to solve, and then you map that equation to the existing arrangement or topology of the qubits, and that helps you solve your optimization problem. So if we try to go into the intuition of the quantum annealing, how it works, see, it's exactly not what is happening, but just the next slide that we are saying is just here to pass the intuition that how annealing is solving a large optimization problem. When we started, we said that an optimization problem, and in some cases might take hundreds of years. A traffic routing problem with large number of constraints might take multiple weeks, multiple years to solve. Now, how does annealing work here? So you set initial state of the qubits. You have large number of qubits and you set the initial state. Then you have an energy function passing the energy, just giving an analogy here. And then then that energy function is works based on the topology that you had or the equation that you had defined. And accordingly, the energy changes the state, energy passes the states actually. And you know that where to find the local minima or local maxima. So you know how to optimize your statement for the minima or the maxima. And it is very, very easy for you to optimize, get the optimal answer of the equation. While if you try to do the same optimization with large number of constraints in the classical computer, you'll have to write a big algorithm, many iterations, recursion, that will take huge time. That makes it unsolvable on the classical computer. While this approach actually helps you solve a very complex equation in few minutes only. So this is the intuition, and that is why quantum computers can solve large problems very fast, because it is not working on the classical 0-1 case. It is using this phenomena to solve your equation. Now you can decide your equation, and this is the one example that you may have different qubits in different fashions joined together. That is called the topology. And then how you map your problem on top of that is your expertise there. Now, how to solve problem in the annealing case? You have to define your problem in an equation format, which is called QUBO, quadratic unconstrained binary optimization. Just take the example of finance or logistics or some other industry use cases, like we said, portfolio optimization or option pricing or vehicle routing. So you know that what will be the equation. With the constraints, that equation might become difficult. Then you need to either minimize or maximize. So your major time and effort goes in defining the right equation. Then as a next step, you go and map this equation, you program this equation in code, and then you map it to the existing topology. And then when you run on that existing topology, the problem equation is solved and you get the output. So this helps you solve some problem for some industry problem for you. So this is the second base that we talked about, where in the first case, we said that people are trying to solve some inherent problems in the quantum computing, where we said that, okay, people are writing the algorithms for error detection, error correction, and many more, or maybe they are writing new algorithms for quantum computers. But this now maps to the functional requirements of the industry, where people try to define different problems in the functional equation, and then they try to solve it using the quantum computers like annealers. So now when you are deciding your problem, you can choose which way you want to go, whether you want to solve algorithms on the quantum computers, or you want to solve some functional problem, then which technology to use, whether you want to go for universal gate-based solution or you want to go for annealer system. So when you are deciding your problem, you can choose it which way you want to go and how to solve your problem. Now, this was some idea. couple of examples. Traveling salesman problem on the optimization. So in the link, if you see, there is an example which solved actually traveling salesman problem. And if we go into the computer science theory, we know that this is an NP-hard problem in the classical system. And you need to find out the shortest possible route where people or a person visits each location once and also passes through the route once. Now, this is an NP-hard problem in the classical computer, but if you try to define a QUBO for that, and if you try to map it on an annealing system, then you can solve this problem. Now, what type of constraints you have? Maybe there are some weights, maybe there are some restrictions, times. As you keep on adding more challenges, it becomes even more difficult. But here, it's like how you define your equation and how you solve it further. Exactly same problem if you go in another industry is job shop scheduling. Same way, this is also an NP-hard problem. You have to find out the schedule on the machines that may minimize the making span of the project. Taking the constraints, for example, this equation, this example where we see this problem has been solved, takes some constraints. For example, it assumes that each task starts only once. It might happen in your use case, task might pause and might start, or maybe multiple tasks can run in parallel. They can run in equation in sequence, or maybe multiple tasks can run in parallel. And when we say multiple, means maybe 2 tasks can run in parallel or 5 tasks can run in parallel. Depends what constraint you have. Then each task here, it assumes that should follow a particular order. For you, it may you may have a dependency or not have a dependency. Accordingly, you can change your equation. You can run one task on a machine, or maybe you can do parallelism on a machine. Task time must be possible, means different kind of constraints that you have. Based on that, you can define your equation and try to solve. Exactly some other problems, bin packing problem, when you are trying to pack some items for a home delivery or for shipment. If you have multiple containers, you want to pack multiple boxes, you want to pack them into a container so that they can be shipped together. Now, example is, take an e-commerce organization where you might order something on Amazon, you might order something on Flipkart, and they want to ship your order together. So how should they pack your orders together in a box? Or maybe you look at a shipment company like Merck's, who is running containers, shipping containers between countries, and they are transporting large boxes. So how should they fit the boxes together so that they can optimize their space, they can optimize for weight? There might be some constraints on the weight level constraint, legal constraint, compliance constraint. So how to manage those constraints, and what should be the optimum level for the cost and the route? Slightly different variant of the traveling salesman problem. In traveling salesman problem, it was like finding the shortest route. But here, just take an example. There is a pathological lab where they collect the blood samples, and they have to take that blood sample to the central pathological lab for testing. So before the blood sample contaminates, and they also have to optimize that one person can collect multiple blood samples from multiple locations. So all those things, constraints put together, there might be some routes which are closed or open. How much time per route is there? So many constraints put together, but this is a typical business problem that someone would want to solve. Now this is where we set the context, where the quantum computing is right now in the industry. What problems can you solve? Now, once you have decided how to move further and how to solve those problems. Now, what is the current technology landscape? Here, I'll take the example from AWS. So we did talk about multiple quantum computers, like some are gate-based, some are annealers. But the challenge is, if you are writing some code, for example, you choose to write code for a gate-based system. So we understood that, okay, there will be some operations on different qubits you will apply. But now suppose you started using computer 1, quantum computer 1, you wrote your code, and then you decide, no, this computer is not good enough, or maybe I want to try it on some other computer. So you will be writing your code on using one computer's SDK, their own operations. Now, if you have to change, you will have to learn completely new thing, change your code. That's a waste of effort. That is where Amazon Braket comes in. So in Amazon, in AWS, you have multiple services. Some are for compute, storage, databases. But now Amazon Braket is a service which gives access to the quantum computing hardware, quantum computers. Now, there are multiple quantum computers. There are 6 quantum computers that AWS offers under Braket. Now, Amazon Braket is very well integrated with the other services. Now, if you are building some website, web application, or maybe some database related solution, so you know that there will be some security, some compliance related things that you would want to do, because Amazon Braket is very well integrated in the cloud. So all those things of security, integration, technical support, everything is handled by Braket. I mean, you get that benefit. Now, next, because it also gives you a wrapper over the quantum hardware. So you decided, for example, IonQ is a gate-based system and Rigetti is a gate-based system. Now you choose to write some code for IonQ. If you have to change it to Rigetti, if you use the standard SDK given by IonQ, then you will have to change your entire code to go to Rigetti, and you will have to learn the new SDK. And again, if you want to run it on both systems, you'll have to maintain 2 codes. Braket gives you a wrapper, so you can choose to write your code in Braket SDK. Now, it's just 2-3 lines of code change. Today you say that, okay, you want to run it on IonQ. Tomorrow you say that you want to run it on Rigetti. Your same code will work. So this also solves that problem. Second, on top of this ecosystem, you have, because it is very well integrated with the cloud ecosystem, so you have large number of enterprises giving support, many solution providers also giving some solution that you can use for your end solution. Many researchers, many educators are trying. Plus, because it is very well integrated with the other cloud ecosystem, so for your quantum solutions to integrate with your regular business application is easy. Suppose you have a logistic problem, like you said, you solved some logistic problem, traffic routing, but now you want your business solution to use the traffic routing solved by quantum computers. So your business solution can very well be integrated with the quantum computing solutions using Amazon Braket, because Braket is part of the cloud only. Now, in Braket, you can build your solutions. That means it gives you managed notebooks. You can have Jupyter notebooks, many already accessible examples available on the GitHub. You can test your solution on the simulator, and then you can finally run them on the real quantum computers as well. And at the same time, because it is part of the cloud ecosystem, so you can monitor the progress. You can manage the logs, you can see who, all security related aspects, everything put together, ready for your business solutions using the quantum computer. So how does it place? So AWS Cloud has multiple services. One of them is Amazon Braket, which is offering access to multiple quantum hardware. This is giving just an example of 3, but there are 6 different types of quantum computers. It also gives you simulators on the cloud. It is very well integrated with other cloud services, where for monitoring, notification, just taking an example, the service like CloudWatch, you want to use storage, so very well integrated with the Amazon S3, which is storage service. You want to ensure the permissions, access management, so IAM, and you want to ensure the encryption of the data, so KMS. So some example, but it is integrated with many more services. On the other side, it also is giving managed notebooks. It is giving a local ID. You can set up the Braket SDK on your local laptop, or maybe you can do this stuff on the Braket console through GUI as well. So you can access Braket and write your solutions, test your solution, and effectively run your solution there. Now, we said that there are 3 systems, but there are actually 6. So these 6 systems, D-Wave system is an annealer system. Rest all 5 systems are universal gate-based system. Now, these quantum systems, for the underlying qubit level behavior that we talked about, they use different technologies, and these different technologies may give different level of stability, different level of consistency on the qubits. So IonQ has been built using the ion trap technology. These both Rigetti and OQC are using superconducting, and Xanadu is photons, and this is Rydberg ion. So different types of qubit system offering different number of qubits. So it's starting from 11 qubits to going up to 80 qubits systems, and annealer system also offering 2000 qubits and going up to 5700 plus qubits. So single interface for multiple hardwares. When we talk about the simulators, again, multiple simulators for solving multiple problems. So 3 cloud-based simulator offering multiple qubits, and a couple of local simulator. That means you can simulate quantum circuits or quantum systems on your laptop or on your local system as well. So you can choose which system to use for your application, which use case to. So first, I'll say that you have to decide your problem that you want to solve, and then you have to choose which technology, and then after that technology, which system to use. So all those things you can decide when you are going to submit your problem for your hackathon, or you're going to build any solution there. Another point, we said hybrid system. So Bracket also gives you option of creating the hybrid jobs, where when you are submitting a job, some classical CPU is made available where your application runs. And this classical CPU is very well integrated with the quantum hardware. So you might write an algorithm, say with 10 steps, and you know that step number 2, step number 4, or step number 8 requires some kind of quantum computation or some kind of chain iteration. So you know when to invoke a quantum computer for some execution. So that integrated classical CPU and the quantum hardware integration in the simulator or the hardware is also possible with the Bracket. Now, some common jargons that you will come across. So when you create a network or a circuit, as we say, so when you submit that circuit for the execution, that submission of a circuit is called a task. So that the central piece, as we say, is a task. Now, we said that these quantum systems are not error-free. So how you get how you ensure that whatever calculation you are getting is error-free, or some kind of error correction or error detection has been taken care of. So the one solution, or I mean how quantum systems take it is like, when a task is submitted, you also specify number of shots. You say that, okay, this circuit you execute for 1000 times or 500 times or something. So that number of times, as you say, is called shots. So you may say that, okay, run this circuit 100 times or 500 times. Now the same circuit will be executed 500 times. That means for the 500 shots. Now you know that there is the output on every execution might be different because of this error nature, but effectively it will create a distribution. So you know that on that distribution, what is the maximum expected value, or what is the maximum value, and then you can choose that value. And it gives you the output based on that shot. So it creates a distribution, and you can take the value from the distribution to get the best output out of that. Now, this is the task and this is the shot. Now, when you are submitting a task, it might happen that it requires multiple iterations. So there comes the job. So when you create a job which might require multiple iterations on the quantum computer, so job actually has multiple tasks, that means multiple execution, and task has multiple shots. So how many times each task will be executed? So this is how they are related. A top level thing is hybrid job, where you have classical and the quantum computer, and you need iteration. Every iteration is called task, and in every task you run the circuit multiple times. That is called shot. So these are the jargons that will help you write your code or write your solution on quantum system. Plus also at the same time will help you estimate that how much resources you might need for the hackathon. Like Reena initially said that you will be given some access to the quantum computers, but you need to know that how much resources will you need. So this will help you estimate those resources when you're submitting your job. Now we did talk about the Bracket hybrid job. So this is how they work. Effectively, you will have a job instance, a container, a classical compute coming up. This compute knows that whenever you are running a quantum computing job, it will know that when to start a simulator, and when the job simulation is done, it will shut down that. And also at the same time, this classical CPU or classical compute will help you integrate or use the other AWS services as well. And from this compute, you can access the external processors as well, quantum processors. Some other examples of the external integration. So you have, you can, in classical world, you create applications which are API driven. So you have APIs where your system makes call to the API and the execution happen, API returns the result. Here also you can have a cloud-based API gateways. again, cloud-based authentication, user authentication, other services. Now you can have an API in front of the bracket. So this is where the integration comes. Bracket is very well integrated with the other computing services. So one integration is like you can have an API gateway, which at the back makes call to a quantum computer. That means you can expose your quantum computing application as API to the external world. So just an example that what does this integration bring out. Similarly, you might want to have an event-based application. So there also same thing. You can have an event bridge which triggers something on an event. So it can trigger a job at the bracket, a quantum job simulation or on the quantum hardware. Also at the same time, output of the quantum system being stored in the database, being used in machine learning, analytics. So very well integrated for the event-based applications also. Finally, if you want to do machine learning on machine learning using the quantum computing system, so like for machine learning on the classical systems, you have frameworks like TensorFlow, PyTorch. Now there is a framework called PennyLane, which very well integrates with TensorFlow, PyTorch, and also integrates with Bracket. That means you can have your TensorFlow, PyTorch related machine learning networks and leverage the quantum computing for your machine learning. So it brings the machine learning world on the classical computer with the quantum computer. So PennyLane allows you that. So overall, I'll say that the current ecosystem of the current quantum computing ecosystem is like you have some well-defined, well-solved problems. Similar ways, you can think that in which area you want to go. Choose your problem that you want to solve. Then you choose that which technology you would want to use. Then choose the right hardware for that and the right framework for that. So these are the steps that you can follow. And then accordingly estimate the stuff. When you submit your ideas on the hackathon, sorry guys, when you submit your idea, the resources that you're looking out for, will try to give those resources so that you can build those solutions on the hackathon. So this is a brief overview from our side. So any queries, questions that you have now open to you.
So there are some questions which have been answered already, but there is one question which is not been answered, which says, can we integrate AWS RDS with Bracket? A question by Aditya.
Yes. So see, Bracket direct. Yes. So in the Bracket hybrid job, yes. So you have a classical compute there as well in the Bracket hybrid job, where CPU and the computer there. So from that classical compute that Bracket gives you, you can make call to any AWS service that might be RDS as well.
Hello, good evening. Am I audible?
Yes.
Thank you. It was a very nice, good session. Actually, like we propose one quantum safe, I can say post-quantum cryptography. Our algorithm is mainly on digital computers only, classical computers only.
Yeah.
Not with quantum computers.
Which is fine.
So now, yeah. So now, like we want to know, because I'm new to this quantum domain. I'm a cryptography cybersecurity engineer. So I want to know, like the heavy computation, whatever we do in our classical computers, can it be mapped directly with quantum computers, or should we write our own code for that?
So
can I answer that question, Sachin?
Yeah, please.
Yeah. So I think, so first of all, post-quantum cryptography is classical solutions only. It is those algorithms which are going to be secure even when we have a scalable quantum computer. But the solution is classical. It is not quantum in the PQC algorithms that we see today. Maybe 50 years from now or 20 years from now, when we have new algorithms evolving, we may have quantum, post-quantum algorithms which are quantum solutions. But today, all the PQC algorithms are classical solutions. So you have to work on them in the classical, put the solution in the classical format only.
Yeah, that's nice, ma'am. You have answered well. Actually, like ma'am, NIST already they have announced, right? Kyber.
Yes. Yeah.
post quantum. So that understanding we do have, like we can do only with classical computers, right?
Yes.
But just
And most,
uh, out of curiosity only, I'm asking, if suppose if you have some one cryptography algorithm, can we test with any simulator, like in quantum simulator, just to
see
make any performance?
whether it can be broken or not. Actually, if you look at the context of those algorithms on NIST, you will see
Mm.
the use cases and the mechanisms that have been used to try to break them.
Yes,
That
ma'am.
may not be in the scope of this hackathon, but
Okay.
because we are asking you to build we don't want you to invent a new algorithm.
Mm-hmm.
If you do something and you present a a proof of concept, we will
Mm-hmm.
that's all you can do in this time frame. Testing it against quantum systems is
Mm.
then a bigger effort, and you have to take maybe QETCI can help you get the right kind of involvement
Yes,
for
ma'am.
something like that, right?
Yeah,
But
ma'am. One more. Yes, ma'am.
but
Yes.
otherwise the PQC use cases would look like this. Because these
Mm.
algorithms are already finalized by NIST, you have open source versions available for all of those algorithms. So
Yes.
if you pick up one of those implementations, let's say, and then you want to demonstrate a use case, could be, let's say, how do you develop a messaging system which is completely post-quantum secure? Or how do you have an email system which is post-quantum secure? How do you have an e-commerce system? I'm just randomly speaking here. But
Mm-hmm.
implementing those algorithms in the current context, or another use case could be you take up a peek, you look at existing systems, you see that RSA today is deployed, at different levels of the stack and in your communication systems also, right? So how do you address either one particular stack, or how do you create a generic tool which can help people migrate from existing RSA to post-quantum cryptographic algorithms? These are all various use cases that could be very, very useful for people, right?
Yes, ma'am. Sure, ma'am. Thank you, ma'am.
All
Thank you, ma'am. Last one question, ma'am. Last one question, right?
Sure.
So there is something called max depth analysis they do to check whether the proposed cryptography algorithm is quantum safe or not.
Right.
So for max depth analysis, we have found some code in QSKID. So of course, our team is working on that.
Okay.
So in that direction, if you could provide some input to us, it will be a great help. Generally, also.
So what kind of input are you looking for?
That max depth analysis. How
You
they
want
perform.
somebody to
Yeah, ma'am.
to provide mentorship on that?
Yes, ma'am. Mentorship.
So,
Yeah, max depth analysis.
So here's the challenge that we have. Today, we have two companies that are supporting platforms along with the hackathon, which are providing supporting platforms, and that is AWS, Bracket, and the other is Microsoft Azure Quantum, right?
Okay.
So most of the mentors that we have from a tech perspective are from these for these platforms. We allow people to submit ideas and work on other platforms because whatever you are comfortable with, you should work on that. But my recommendation in a scenario like this is you reach out to IBM and ask them for that mentorship directly. They are not, they are not supporting this hackathon, and we do not have access to any of their mentors. So I'm afraid that we'll not be able to support that directly. But usually, most other companies, if you reach out, they will provide you the right input. So I would encourage you to reach out to them.
Sure, ma'am. Sure. Thank you very much, ma'am. Thank you.
Yeah.
Hello. Is my voice audible?
Yes, it is.
Okay. Thank you for such a beautiful lecture. It was very intriguing. And I have a question regarding the manufacturing sector in quantum computing. Especially, I want to know if there are any use cases where I can implement Industry 4.0 in using quantum computing. So could you help me in giving some insights on that particular field?
See, Industry 4.0 is a very, very big term, I'll say.
Okay. If you want me to be more specific and technical, I would go ahead with cyber physical systems.
See, I'll just go still on a granular level that you will have multiple manufacturing processes some processes requiring some kind of optimization, means if you are creating some, I mean, if you are, I'll touch upon multiple threads. Actually, there are possibilities. You know that which manufacturing industry are you from and what challenges are you facing. But for example, some of the products might require some kind of quality check, and you know that. So I'll just give an example. Like I won't take the name of the company, but we were talking to some company today, and we discussed with them sometime back as well. In the tire industry, when they so they manufacture tires, but if you know that if you run the car at a very fast pace on the road, it makes sound, and usually the sound while driving in the car you hear is not from the engine, but actually it comes from the friction on between the tire and the road. So they try to cut the tires in different, the tire has different designs and cuts on that. So they try, so what type of cuts should be there so that the air passing between them should be a design, I mean, should be such that no noise is created and you get a noise-free feeling. So that is a kind of optimization, and that's a very tough thing. So people are trying that, can it be solved by the quantum computing? Just giving an example. Similarly, if you have some product which requires some quality test, that could be one. Second, if there is an optimization, if there is a manufacturing process which might take a little longer, so is there an opportunity for an optimization? But again, at the same time, see, does that optimization require huge time and is not classically solvable? That's one. Then some example, like you said, large numbers. I'm going away from the optimization problems. Anything that is dependent on very big number calculation, finding the square root, finding the prime numbers, prime factors. So all those things are the potential candidates for the quantum ecosystem. Machine learning, as we said, you said cyber system. So lots of sensor data you will be accumulating, and you will have huge data to learn from. And machine learning inherently is an optimization problem. So how to leverage quantum computers for getting those maximum, for settling those objective functions of the machine learning. I give you one more example. There is an organization which has filed for a patent for creating an optimal pipeline for machine learning models. So when we say pipeline, they are not claiming, I mean, their focus was not on improving the machine learning model quality, but what they said that with the data that they have, if they train the machine learning model, it takes large number of hours, maybe 48 hours or even more. But with the quantum computing ecosystem, their model converges fast, so pipeline time is reduced. So this is what they have focused on. So that could be one area. So you have to see that what are the challenges are you facing. So an ideal approach could be that you see that what are the possible challenges you are facing in your manufacturing operations or processes. Then we can discuss that, okay, what are the possible quantum solvable problems? And then let's focus on that. And thereafter we'll say, okay, once the problem is identified, then we'll go ahead further that, okay, what technology to use, what approach to use for that.
Okay. Okay. Maybe like I have a field in expertise for condition monitoring for lathe machines and other CNC machines. So could condition monitoring actually takes a lot of time in collection of the data through the sensors. So would that be a possible use case or a possible problem statement that can be used for which is solvable using quantum computers?
Are you talking of, sorry, go ahead.
Please go ahead, sorry.
So are you interested in analyzing the data, the quantum part coming in for analyzing the data or collecting the data?
Analyzing.
Yeah, so how much is the data that you usually end up collecting?
Yeah, we end up usually with 1 to 2 terabytes.
There's not a lot of big data, right? You can use classical systems to analyze it very, very well.
This is on the prototype level, but when we come to the industry level, it goes up to petabytes as well.
Okay, so I think when the data is that big and you're analyzing it, there is some scope of, and you're putting in some AI, some machine learning there, then there is some scope for actually bringing in quantum machine learning. It depends on the type of the data and the kind of problem you're trying to solve. When we say quantum machine learning, it's also a very large, it's not a one type of solution that fits under that category. As Sachin was giving you an example of how the pipeline itself was being worked out in a better manner using quantum. Similarly, for different kinds of problem statements, you could see where do you, what stage of the machine learning you optimize on using quantum, right? So I think there could be possible use cases there. Very difficult to
Okay.
say generically just like that.
Okay, okay, understood. So, would there be just this is my last question? Would there be a possibility that can we use the like digital dashboards and connect that to our quantum systems? Like, since you have mentioned that there is a lot of security and convention, so can we allow certain APIs which are external, not AWS related, where like such as Google Cloud or other cloud systems, where we use those APIs to represent dashboards, and can we connect those external APIs to our Bracket as well, Amazon Bracket?
When you say that external API, see, effectively you would want your API to execute some code at the back in the classical mode, and that classical mode can go to the Bracket and get the things. Yes, you can do that technically.
Okay.
But when you say dashboard, so point here is, look at this. I mean, if we just deep dive into the solution that you're looking out for, so you would want, I mean, are you looking out for like a dashboard opens up, and when you are asking for the data, then some data comes from the quantum system, maybe Bracket. That actually does not look like a pipeline that a business will ask for. It is doable, but that is not a pipeline that business will ask for. Effectively, what business will look out for is that a problem that you want to solve goes to quantum system, it is solved, and the output is stored somewhere, and from that storage you get the information for the dashboard to show.
Oh, okay, okay, I see. Understood.
It's the same thing, right? Today and for the foreseeable future, you're never going to use just quantum computing on its own. All platforms, including Amazon Bracket, are actually make calls to classical as well as quantum systems, right? So within the same program, you'll be making calls to quantum systems as well as classical systems. Like he pointed out, 2 + 2, why will you send it to a quantum system which will give you an approximate error, because it's based on probabilities, right? So you will always use a classical computer to do those kind of calculations. And then you cannot do operator assignment or a variable assignment very directly in quantum computers, right? So when you're manipulating data, where you want to move the data from one data type to another, or one storage to another, or any manipulation you want to do it, which is classical in nature, you do that on the classical computer because it's a lot easier.
Okay, okay, I see. Not an issue. I think all my questions are clear. Thank you so much for your
All
time.
right, thank you. There are some more questions in the chat? No, I think these have been answered. Any other questions? Looks like not, and a lot of people have dropped off, I think. So shall we bring this session to an end? Okay, last call for questions is also over. So I think, Sachin, thank you very much. I think that was a very, very useful session. And this session has been recorded, so we're going to put it up for everybody's benefit onto the Hackathon website, as well as the QETCI YouTube site and the QETCI website. So people have many ways to access this as we move forward. All right. Thanks, everyone.
Thank you, ma'am. Thank you, sir.
Thank you, Reena. Thank you very much.
Thank you all. It was a good session. Thank you.
Bye-bye.